Welcome to Ruby Thursday. I'm Melissa Wanish. This is a recording of the Ruby Roundtable meetup that took place in New York City on November 8th, 2017. At this meetup, Stefan Ort took us through using reflection in Ruby to build an understanding of a system. It was a really fascinating live coding session. Thanks again to our sponsors, ThoughtWorks for providing space, and Flashpoint Intel for providing food and drink. For this recording, Paul used QuickTime to record his screen and voice, so you won't see any of us in person, but you get to see the code up close. Enjoy this recording of the Ruby Roundtable.
Okay, so thanks for having me. Today I'd like to talk about some techniques for inspecting a system using Ruby, using reflection techniques, and the way I sort of stumbled into doing a bit more with this technique recently has been that I'm working on a system that automatically updates Ruby gems, and there's a lot of work that is sort of running commands and inspecting command output, so seeing what happens when you run bundle updates, reading output that maybe tells you installing a new version of a gem, and then turning that into a dictionary that can be used ultimately to generate things like diff URLs and other details about what changed with the gem update. So I was wondering, what other things might we be able to analyze? What if we could figure out the changes to your code that might need to be made with a new version of the library? So this is exploring some techniques to allow you to understand what is going on with different classes and namespaces in a Ruby application. We're going to start off using just showing some of the basic techniques. So I have an editor here with Ruby files. We'll start off in the interactive Ruby interpreter. And if you want to find a list of all the top-level concepts, the classes, and globally available constants in Ruby, you can call object.constants. So there we see things like integer, array, hash. Some of these are classes. So string is a top-level class. Some of the constants might be things like arg v that would allow you to see arguments that might have been passed into the command line application. If we wanted to get a copy of a class from having loaded it dynamically, so if we look at this again, we have a collection of symbols, so we can see array, for example. And if we wanted to turn that into the class array, it would be object.const get array, and that returns the actual class. And on that, we can inspect things like finding what methods are available on the array class, what instance methods are available on array objects. So those are some of the core building blocks that we'll be using for all of this exploration. So let's see what changes when we load a gem. So we're going to begin by having the original.
Comment on the array itself, or do the concept?
So, okay, if you object.constants returns an array of symbols, and you can see that by that all of the items in object constants are symbols. So if we called array.methods, what would we get? What should we get? Methods for a symbol. Yeah. Methods for this object. So if we wanted to get the actual class, we have to do const get, and then const get receives a symbol or a string. So you could do array or array. So we're going to start off by getting all the constants that existed, and then let's require a gem using the JSON Web Token gem, and we can compare the difference. So we'll print out okay. This is original, and I'm going to rename this to updated. Okay, so we have the changed constants. And let's just print out what that generates. So we can see that after we loaded the JWT token, it made digest, OpenSSL, a few other things available. Some of these are from the standard library. So in Ruby, OpenSSL is shipped by default. It's just not loaded, so you'd have to require it, and then you'd have access to OpenSSL. The same is true of JSON, OpenStruct, and base64. But this JWT item looks interesting, so let's inspect that one. So we can see here that JWT was added and wasn't available before. These are the top-level constants. There might have been some new methods as well, so let's explore those. We'll just look at all the methods that were available on every object, and basically print out those changes as well. And we can see that at the very top level, since we've loaded JSON, now we have access to a toJSON method for those behaviors. There are other classes we could compare this on. So we could say, let's look at the original methods for string, the updated methods on string. Similar changes again. So let's dig in a little deeper. I'm going to focus just on the JWT class because we know that these other ones are in the standard library. So on JWT itself, we can call methods like this. And if we wanted to find out what was added from, what was basically the unique contribution of JSON Web Tokens, we could first, let's look at the child items in that namespace. So if we had, let's look at the constants in JWT. And do a similar thing for JWT methods. Okay, let's just see what we get for just this new top-level namespace. So you can see here there are a number of classes in JWT, and here methods introduced by JWT, the ones you'd probably expect for a token library, the ability to encode and decode a JSON Web Token. So let's look at, so this is an example of some high-level analysis you can do when you load a gem to figure out what was added by it and what capabilities you might now have available in your system because of that. This is often useful if you're debugging a system and you're trying to figure out, you don't necessarily know from documentation what is available. You can find out what properties might be available. Now, I'm going to use those techniques now for an example of finding out that something was changed. So here, in example 1, we were finding new things that were added. But what if something overwrote old behavior? There's a way we can do that, detect that as well. So we're going to begin by having an example. So let's just let's use an example of string equality, and we'll start off with with a true example and a false example. So there's one that should be true, and let's do this should be false. So let's run that, and we can see the expected results. So let's load something that changes this. Okay, so we're going to make this new library. And let's just reopen string and redefine string equality. So when you call, say, string, this sends the, or call, it invokes the equality method on the original string object. And we can overwrite that using this. So this is the equality method and receives the string against which to, or the object against which to perform that comparison. So if we wanted to just reverse the original one, we can alias the old method. So now we have the original equality method mapped to old EQ. And we're just going to return the opposite of old EQ like this. So now if we run this example again, we should see this should be false now, and this should be true. Let's see if that's what we get. So now you can see we inverted, we had true and false, now we have false and true. Now we've made this destructive change very directly, so we know that's what was changed. But if we wanted to programmatically discover that change, we could do something like this. Basically, it would be nice to be able to, at the end of this, compare this against the new version. So we're going to build the structure that allows us to make that comparison. We're going to start off by thinking about what this structure is. So we'll have this will be a hash, and the keys in this hash will be symbols, and the values will be themselves hashes with keys for the methods, and we're going to make the value of the second level hash be the implementation of that method. So we'll start off with old being a basic hash. We're going to find all the original constants. And for each of those, we're going to get the constant. And we want things that have instance methods. So we're just going to restrict it to, as I was showing you at the beginning, there are many of the top level constants are classes. Some of them are singleton objects, or things that resemble objects but you can't call. You might not always be able to get methods for something that is a top level constant. So we're going to check first to see if this class indeed has instance methods. And if it does, we're going to say that we're going to build a structure that allows us to capture those methods. So we have the name for the original instance method. So if we go through instance methods, we get symbols again of those instance methods. And if we wanted to capture the implementation of one of those, we just call the instance method, and we get an object representing the implementation at that time. So we're going to capture this method. And this will be class dot. So we get the instance method from the list of all instance methods. And we're going to say that the original instance method for, actually I'm going to change this to, this is really a collection of implementations. And this is for the instance method. That's going to be the implementation that we just captured. And then after we've built this representation, we'll save it into the list. So old so here we have once we've built basically the second level dictionary that contains the method names and the method implementations, we'll save those into a dictionary for the name of the original, or of the top level class. So this would be string, and this is wrong. This should be the original constant. So the original constant is equal to this dictionary. In this dictionary, we have something like that. So now we've built this before making changes. Let's create this after making changes. And we're just going to say everything that was old is new, and everything that was original is updated. Otherwise, the typos can become a bit of a challenge. So we should now have the old and new versions. So let's see what we can discover. We're going to go through each of the old classes. So we're going to go through the old object. And so if we use each on this dictionary, we have, or hash, the languages are not consistent, unfortunately. So if I say dictionary or hash, I probably won't say associative array, but they all are the same thing. So we have the key of this dictionary is, sorry, the top level key is the class. So we have the class, and then this will be the implementations. And to make this a bit more clear, we'll say the class is going to be the same, and these are the old implementations. Now, so now we have string and so we have this structure to work with. We're going to compare the old version to the new version. So we'll have old implementations, and this will be the old. So we need to get at these values. So we have the old method and the old implementation of that method. Now, if we check the new implementation, we can say that it's going to be from the new object, and it's the same class, and it's the same method. So let's rename this as method name. And unless they're the same, we're going to have the class, and this is an instance method, so it's turned out this way. So we're going to say that the method changed after.
Sorry, I missed that. So old has, for the class you have equal implementations of old? Or?
So here, so this, okay, class is going to be string, and the old implementations will be a dictionary of the implementations for all the old methods on the old class. So we have one implementation of each method, but we have many methods for each class. So it's the collection of all implementations for that,
I see.
for the old methods. Okay, so let's try this. So we should see string equality as the output of this. So we have changed string equality. So instance method on string changed. And if we were to do something, so change a different one. Let's see, what's a good other method to change? So we have upcase, downcase, lots of things we could do. We could have we could change the definition of not equal. Not yeah. Maybe let's not do that. So so here we're making use of the string equality method, but we can change other ones. So if we had if we had some, we could just change any of these, and we're not using them, but that shouldn't matter. And we can see here that upcase also changed, so it finds all of the implementations, regardless of whether you're using them.
Question for you: as far as this only determines the methods that previously existed.
Yes.
It doesn't actually show at the current moment if we have new methods added on top of it.
True, we don't. But a way to do that would be to find the, so here, say, something. So we have a new method. So now we can, so these are changed methods. So we went through all the old implementations. So now what we could do is, so we're going to look at it from the opposite direction. So we're going to look at, sorry, this is, we have the new implementations. We wouldn't, so to find out that there were new methods, we wouldn't even need to look at the details of how they behave. So I'll just do a shorter version. So we know that we have the top level classes, the top level keys. So we could say, oops. Okay. So if we had new, I'm just going to use grab the names for this. So we have the new methods will be the keys of the methods, the dictionary that contains the implementations. And this will be so we're going to compare the two arrays. And say and we can say a comparison we could do. So let's look at this. And now we added, now we can see the methods that were added in that class that were not previously available.
Can we figure out if someone overrides equal equals an object?
Can we discover that someone did it?
Can we discover this if someone overrides equal equals an object?
At the top level?
Yeah.
Yeah, it works on any object.
Okay.
So you could do.
Do we have to have new implementation equal equals old implementation work, and if that's overridden?
This is just looking up the availability of methods. It's not executing them at all.
Right.
And so we had, Okay, we could override it and just not do anything. Like we could log something like this, and now we have changed everything. Equality changed all over the place because they inherit from that. Okay, so that is an example of figuring out what changed through monkey patching. Whether you did, you can use that whether you changed it or whether someone else, like whether you know what the change was or if it's coming from some other library. So a third example now is for changes that are more indirect. So we were looking at things that change the behavior of methods, but what if you want it to be available of potential changes, or basically things that might have been added but are not in use yet. So for this example, we're just going to do dictionary comparison. So let's have three dictionaries that we're going to compare. Okay, so we have this, and this is going to be there's 3 objects. So this should be false. So let's start with the control case. I think that's always true. This should be true. This should be false. Let's say this is I'm going to switch the ordering of those. So we have the regular compared to regular, regular compared to weak, and regular compared to agreeable. So this should be true, false, and false. So we have true, false, and false. Just going to add some spacing. Okay. So let's now require a different library. So this new library for hashes. And let's make this a module. And now let's say we're going to have a new version of equality. And this one changes it so that the instead of caring about the full values, we're just going to care about the keys being the same. So the keys of the current object will need to be equal to the keys of the other object. So these 2 hashes are close enough to be considered equal. So we're not making use of this at all. But we have it available now. So if we reopened hash and prepended this new module, we have to prepend it because hash already defines equality. And if we were to simply include the module, it would add this version of equality at the end of the lookup. So Ruby would never find that version. It would always use in the sequence of looking up implementations of equality, it would find one before getting to this one, so it would never use it. But prepending forces it to come first before whatever else it has. So now if we were to run this, we should see true here, but we should also see true on the second one because the keys. So we simply changed the values, but the keys are the same. And of course, this one should still be false. So now we have true, true, and false, where we previously had true, false, and false. So we've made this change. So we knew that this module was available, but we wouldn't know it from the name of the library. So in this final example, let's take a look at understanding the understanding the inheritance or the ancestry tree of different classes. So maybe hashes are they're starting to demonstrate an interest in social climbing, and they want to change their ancestry because it's not quite good enough. So here, let's see how we might change ancestry. So we have the again, we'd like to compare. So let's say we have the old hash, and we'll just have this be an array of various ancestors, and so on. So we could say O is going to be a dictionary again, and we're going to get the constants once more. And for each of these constants, we're going to check to see whether it has ancestors. So if it can have ancestors, we're going to capture its ancestors. So we're just saving a list of ancestors. In this case, string ancestors has a collection of classes. Yes, so these are not symbols anymore, so we don't have to do the when we store these values. These are the actual classes, which could be useful if we wanted to drill down further. So here we have a list of all the ancestors for all the classes, and we're going to build that again after making this change. This is just building the list 12 times, and now we have so we have old, basically printing out when there's a difference. So we can go through, so for the old class, we have its old ancestors, and then we can find the new ancestors. And let's say we're going to find the ones that were added. So we're going to show all of the ancestors that appeared in the list that weren't there before. Okay, let's run this. So we can see that hash now has close enough, where it didn't before. And that's true only because we made use of it here. So here we should now see that there were no changes. Now, this allows us to see that a gen that we've loaded has maybe added behavior to a class that we're using through module inclusion, or extended the scope of available things in a class through the use of modules. We could inspect things further, and for the sake of time, I won't go into all the details, but if we were to find all the new classes that were, or find all the new modules in the system, then we could check to find, basically find all the classes that don't that have it as an ancestor, and sort of find, basically you can sort of do it in reverse, right? So start from the, actually, do we have 5 minutes to?
Go for
5
it.
minutes
Yeah.
to check this example. So, okay, so we have this new module called close enough, which which we have used in hash. Okay, so if we wanted to go through and basically find the new modules that that exist in the system and aren't being used, we could first. So we can still use the ancestry list because that's what's going to tell us that's not being used. What we're going to do now is go through the new constants again. So we should still have these updated constants. So okay, this is going to require some analysis at both levels. So we have the old unused modules. Let's just do this. And we're going to go through, so this is for finding ancestors. Okay, so we need to have, we're trying to build a list of, we're going to find all the modules and then find the ones that don't exist, or that aren't being used. To avoid, so we're already going through in one loop, and we're going to do something that compares another set. So I'm going to start here and just do, just capture the modules first. So if it is a module, I'm just going to append it to the list of old modules. Now, we've built this list of modules, and we can have old unused modules be an array. After we've gone through all of the constants and populated the list of modules, we can have let's just look at all the modules that aren't being used by other classes to simplify this a bit. So if it is a class, then we're going to append it to that list. Okay, so the reason for that limiting is that so we can be sure that when we're checking for ancestors, we don't try to find, we don't get into the situation of trying to find that a module is not related to itself. There's some tricky things that might come up with trying to loop through these nested objects in this way. So we're just going to go through all the old modules and then look at the old classes. So here, let's just say the descendants of this module. We go through the old class and check to see see if its list of ancestors includes this original module. So now, old unused modules, we'll say I'm just going to append this old module to that list of unused modules. Assuming that I've typed things consistently, I should be able to just replace this entire block with the new. So let me do that. If not, we can undo. Okay, so I'll put this here. And just make this work in the new context. Okay. So now we should have the new unused modules and the old unused modules. So let's start just looking at the new unused modules. And see what we get. And so there aren't any new modules that are unused. So we have this new one. Let's stop using it. And we still don't have a value here. Let me check on this. Okay, so it did find that new module. And so let's see here. This is a new thing I just decided to add on for the moment. So everything else has been done like 10, 20 times live. This one, not. So, well, that's probably like 10 times the other ones. We can see here that we found this as a module, and so that we're reaching that. The thing I'm going to check here just to make sure is that we are passing it to new modules. We're going through each of the new modules, and we have the descendants, and we have new classes. Okay. Oh.
Thing at 80 or no?
Yeah, sorry. If it's empty, then we need it to be a new unused module. So it's the opposite logic there. Yes, so this needs to be an if descendants are empty, then it's an unused module. Okay, yes, so that's more like it. So there are a number of things that are there, but we really only care about the modules that were not present in the before the changes were made. So we can say the diff unused modules would be the new unused minus the old unused modules. Okay, so we're going to say that. So we have this diff that will list. And there are more things, yes. Because this, I'll have to figure out a better and more compelling thing. But you can see here that close enough is one of them. And if we were to add more, okay, so we just added a few. And so now we have some new unused modules that were there. So with further, so with a more rigorous approach, it would be possible to isolate which ones of these were truly added by, or which ones of these were added exclusively by the newly loaded libraries, with some further more detailed analysis that I'm not able to do right now. So that's basically all I had to show for today. And one use case that I've developed to some extent, and I'm working on automating, is the idea that for any new version of a gem, it would be nice to be able to see things like all the constants that were removed, the constants added, the methods removed. So here, this was a real example from going from Rails, last version of Rails 5.0 to 5.1.0. So showing you all the things that were added and removed. And think about one place you could go from here is if you know the methods that were removed, you could monkey patch all of those methods and log to see that you're using them, and basically automatically generate a report saying if you're going to upgrade your gem or upgrade to this new version of the library, you need to take a look at these places in the code where you're using the old methods. Another sort of perhaps more ambitious possibility would be if you have a list of all the methods that were changed in the new version, you could log basically add some monkey patching around the invocations to log the values that were passed in and the values that you got out of those methods, to be able to write out basically a baseline for testing to automatically generate tests to verify that the results that you got match the results that you get now. Sort of automated testing of your dependencies. So that's where I'd like Dependable to go, but that's a bit down the line. But that sort of work is built into the language and the tools for reflection, and you can make use of that in some debugging, or if you're just in a Rails console and need to figure out what might have happened with a particular object. Some of these tools might, I found them helpful in troubleshooting production issues at times. For further information, I highly recommend some of these resources. The Well-Grounded Rubyist has a number of chapters on, or has a section describing reflection, and also has a good overview of how method calls work in Ruby. Also, the metaprogramming book is valuable, and some of these talks have live examples of making use of some of these techniques for building a test framework, or for demonstrating the lambda calculus using dynamic features in Ruby. That's all I have for today. Thank you. And are there any other further questions anyone might have?
So review again what Dependable does now.
What it does now is it constantly checks for new updates to gems, and it shows you, it allows you to set for each gem the level of updating. Basically, it uses the levels of semantic versioning, so major, minor, and patch level. It also allows you to have whitelisted gems or blacklisted gems. So blacklist would be if you don't want to upgrade at all, or whitelist if you're always fine upgrading to the latest version. So it does that, has a UI for managing that. It defaults to what's in the gem file. And it constantly runs, basically checks for updates and runs them against your test suite. And if the tests pass, it opens a pull request. If the tests fail, it reports an issue on GitHub. Sort of the bare bones workflow right now. So it's already working for Ruby applications. And that's sort of what I'm currently focused on. So making it work better for more use cases, generating more analysis of. Basically, the goal is to help teams evolve a code base in a safe way. So a lot of times we build it because we have a lot of customers that have old Rails apps that we're maintaining for them, and it can be a pain to keep things updated. And so sometimes we might come in every few months to work on a project for a while and have a significant amount of time relative to the overall project just spent keeping things current. So we had something that was doing it automatically for us all the time that would save a lot of effort. And so we're using it for some of our own clients, and it's also open for other people to use.
Very cool. I have some old code bases. I know I had played with it before, but I think I didn't really put it into a project yet. So that's inspiring me to put it in and put it to work, because that's definitely, it's old. Is this you?
No, it's not.
Which one are you?
Interesting. There's another. Okay. It's just dependable.io.
Ah, there we go.
Any other questions about?
Okay.
One of my questions is, I guess, is this the fastest way we could determine these things? Like, does it take a long time? I don't know. We witness it happening immediately, right? But like, if we have we're going back and forth checking all these dependencies, is that any concern as far as like testing wise?
So.
I don't know. There's literally nothing I can think of.
Okay, so so one thing I should say about all these techniques is they're very powerful and Ruby makes them available, but it's probably not a good idea to use it in production code for the most part. So I would see a lot of this is useful for tools that are analyzing your code, or if you are debugging something and are trying to understand details about what happened in runtime.
Sure.
So for that, those features are not necessarily very fast, but again, maximum speed is not exactly what Ruby's known for. So I think the relative performance, I think it's reasonably fast for running commands in an environment where you're trying to inspect things.
Sure.
I would not use it for a main application workflow, unless you're building an app that is specifically designed to do that. Then it's a little different. Well, thanks for listening, and I'm. If you want to reach out to me, I can post the Markdown documents and definitely available online for any follow-up you might like to have.
Thank you. Thank you,
Thanks,
Paul.
that's
Thanks.
Yeah.